Hello, this is Mr. Best. Welcome to part 2 of graphs of functions. We're going to talk about step functions today and identify even and odd functions. The first thing is, what is a step function? Well, one step function that we talk about is the greatest integer function. It's denoted by the double brackets and defined as the greatest integer less than or equal to that value of x. So you can see we're going to graph just the parent function f of x equals the greatest integer of x. And so I got a couple different things that we're going to plug in and identify as to what the answer is. So if it's f of 1 and you plug 1 in, the question is, what is the greatest integer less than or equal to 1? Well, since it's equal to 1, we can just say it's 1. But what happens when you start putting decimals in, like 1.1, 1.2, 1.3, in this case 1.5? Well, what's the greatest integer less than or equal to 1.5? So here's 1, here's 2, here's 1.5. So what's the greatest integer less than or equal to 1.5? Well, 1.5 is not an integer, so you got to go to the left to find the greatest integer less than that, okay, which is 1 again. And even at 1.999, all right, or really even close to 2, it's still not 2 because it's less than that, so it has to be 1. So everything between 1 and 1.99999 is always going to get back to 1. So your answer at the end is always going to be an integer. So what about f of 2? Well, the greatest integer less than or equal to 2 is 2. 2.7 is 2. Negative 3.2, be careful, you have negative 3, negative 4, and we'll put negative 2 on the other side. Negative 3.2 is right here. What's the greatest integer less than or equal to that? Well, less than is negative 4. Same as negative 3.5, and then negative 4.1 would be negative 5. So you're always going to the left, that integer to the left of that value, unless it's an integer itself. So what happens when you plot this? So f of 1 is at 1, f of 1.5 is at 1, f of 1.999 is at 1. So all of these values are at 1 until you get to 2, and what happens? It jumps up to 2, and then 2 all the way until you get to 3, and then it jumps up. And it takes these steps every time it gets to a new integer. So how do we graph this? Well, at 1, it is 1, but when it gets to 2, at x equals 2, the answer is not 1 anymore, it's 2, so it steps up. So you have an open circle at 2, 1, and then at 2, 2, you actually have the value. Same thing, at 2, 2, there's a point, but then at 3, it's not at 3, 2, it's at 3, 3. And so you're always going to have this open circle where that next step is going to occur. And there's your greatest integer function. What's the domain of this? Well, you can plug in anything you want. So your domain is all real. Your range is a little different here. Your range is only going to be an integer. So we can't really just list those numbers out because they go on forever. So we're going to actually, and you can't use interval notation. So we're going to use set notation on this one, and we're going to say x such that, so all values of x such that, and then we're going to explain. We only want integers. So we say x is an element of the integer set. And if you remember the integer set, it's the z. I'll do my best one here I can. And that's what it looks like. So the way we can read that is the set of all x such that x is an element of the integers. And so if you have any questions about that, we can talk about it in class, but that's another way that we can use, instead of interval notation, set notation to identify that. So that's graphs of functions, specifically step functions and greatest integer function. Here's a couple examples we'll look at the end of the notes. The next thing, all right, now we will start the examples, going back to example 1, graphing the step functions. We'll start with f of x equals the greatest integer of x plus 1, and once again, these will be double brackets. Sometimes you use single, but we'll use double there. So what we're going to do is kind of get this idea of a t-chart. And there's a couple ways you can do this, but kind of the way that I think about it is if I plug in 0, I get the greatest integer less than or equal to 1, which is 1. But what happens when I plug in 0 all the way up to 0.99999? Well, I still get 1.999, which is still 1. So no matter what value from 0 to 0.99, I always get an output of 1. Once I get to 1, it steps up to 2. So anything from 1 to 1.99999 will give you an output of 2. And you can kind of keep the same idea going. If you go to 2, it jumps to 3, but that's anything from 2 to 2.99999. And once you get a couple in there, you can go ahead and graph. So when x is 0, your output is 1. And everything from 0 to 0.999 is going to be 1. And then it's going to step up. At x equals 1, it steps up to 2. And everything's 2 until it gets to x equals 2. And then at 2, it steps up to 3. And so you can just kind of keep that same process going. Once again, make sure you get that open circle at the end of that value there, because there's not a point there. There's not a point at 1, 1. There's a point at 1, 2. And there's your step function. And there you go. On the second one, you can try it on your own, or you can watch to see how this works again. I'll do the same thing. So I'm going to do x and g of x. And I'll kind of start the same way. If I plug in 0, 0 times 2 is 0. 0 minus 1 is negative 1. But it's not just 0. It's everything from 0 to 0.99999, because the greatest integer less than or equal to 0 or 0.999 is always going to be 0. 0 times 2 is 0. 0 minus 1 is negative 1. But once I get to 1, the greatest integer less than or equal to 1 is 1. 1 times 2 is 2. 2 minus 1 is 1. But that's everything from 1 to 1.99. 99 keeps going. And that will be 1. And then from 2, it steps up. So that will be 4 minus 1 is 3. But that's everything from 2 to 2.99999. And you can see the y value is going up by 2, and that has to do with this. And we'll talk more about transformations, but it's stretching it out. So we can go ahead and graph this. From 0 to 0.999 is going to be negative 1. So from here. And then at 1, it's going to jump up to 1. And at 2, it's going to jump up to 3. And then at 3, it's going to jump up to 5. And so on. And that's your greatest integer functions. The next thing that we'll cover is even and odd functions. If you take a look at these two functions, the first one being an even function, even functions are symmetric to the y-axis. Okay? So take a look at your ordered pairs. What is the difference between your ordered pairs when something's symmetric to the y-axis? It reflects over the y-axis. Your y values do not change. It's your x values that change. So it goes from x to the opposite of x. And that happens for all points, not just, 1 point happens for all points. Look at your odd function. Odd functions are symmetric to the origin. So symmetry to the origin actually rotates it 180 degrees. So what happens when you rotate it 180 degrees? Look at your ordered pair. All right? Your x value becomes the opposite of x, and your y value becomes the opposite of y. So we're going to talk about how to do this algebraically, but graphically that's what you're looking at. Now, symmetric to the x-axis, you can see on the bottom here, I have it kind of boxed in. Well, the reason is symmetric to the x-axis is not even a function. So we don't really talk about symmetric to the x because it's the x that stays the same and it's the y value that becomes opposite, which means you have one x value going to multiple y values. So it's not a function. One of the things I want you to think about, though, is what is the only function that is symmetric to the x-axis? So there is one function that is symmetric to the x-axis. We'll see if you can figure it out, and then we can talk about it in class. The next thing we're going to do is talk about even and odd functions algebraically. How are we going to prove something's an even function and how something's an odd function? So if you think back to the graph, you'll be able to see this. A function f is even if, for all your x, f of negative x is equal to f of x. So think about that. When you plug in negative x, your output is y. Go back to your graph. When you plug in negative x, your output is y. And if you plug in x, your output is y. So that's how you prove algebraically that the function is even. If you look at the next one with an odd function, if you plug in the opposite of x, you get the opposite of y. So if you plug in the opposite of x, you get the opposite of y. Once again, go back to the graph. Opposite of x, opposite of y for that symmetry when you rotate it around 180 degrees. So that's why these work the way they do algebraically. So I know some of you want to memorize that, but if you actually think about what's going on, it makes sense based on the graph. Okay? And then once again, something to think about, we can talk in class, is what is the rule for symmetry to the x-axis? Even though we're not really going to talk about it because it's not a function, could you create a rule to say, hey, this relation is symmetric to the x-axis? So once again, give you something to think about we can discuss in class. And the last set of examples that we're going to do are these functions even, odd, or neither? So to go through and prove this, you want to identify even. Remember, when you plug in the opposite of x, you should get just the y value, which is f of x. If it's odd, when you plug in the opposite of x, you should get the opposite of y. So that's how you're going to prove whether these functions are even or odd or neither. Now, if you think about an even function, it's symmetric to the y-axis. This is a quadratic. All right, think of the shape of a quadratic. Is that going to be symmetric to the y-axis or symmetric to the origin? It's going to be symmetric to the y-axis if it is symmetric. So really, you can pick and choose which one you want to check first. On this one, I'd say let's check even. So we're going to plug in negative x wherever there's an x and see if that equals the original function of x squared plus 1. Well, when you square negative x, you still get x squared. So on this one, you have proven that f of x equals x squared plus 1 is an even function. So we know it's even, and the reason we know it's even is because f of negative x is equal to f of x. Alright, so for part B, we got g of x equals x cubed minus 1. Once again, if you picture what the graph looks like, is that going to be symmetric to the y-axis or the origin? Well, more to the origin, not the y-axis. So if I was, going to guess which one it might be, I would do odd first. So I'd say f of negative x has to equal the opposite of f of x. So the opposite of x has to equal the opposite of y. Plug in a negative x wherever there's an x. And then on this one, you do the opposite of the function. So it's negative the quantity x cubed minus 1. So on the left side, if you take negative x and cube it, you still get negative x cubed. So that's negative x cubed minus 1. On the right side, when you distribute the negative, you get negative x cubed, but you get a plus 1 instead of a minus 1. So these are not equal. So it is not an odd function. So if it's not odd, do I have to check even if I know that the graph looks the way it does? The answer is yes. You still need to check and prove that it's not even. So we would say f of negative x, is it equal to f of x? Well, we already did f of negative x, which was down here. That was that one. So we already know that that's negative x cubed minus 1, and the original function was x cubed minus 1. So you can see that those are not equivalent as well. So this is neither, because neither one shows that they are equal. And now the last example is another cubic. So once again, if I was picking, I would pick odd first, just based on knowing what the graph is going to look like. So I'll do, once again, f of negative x, if it's odd, should equal the opposite of f of x. So we'll plug in a negative x wherever there's an x. And then we'll do the opposite of the original. And so negative x cubed is still negative x cubed. And then you have the opposite of negative x, which is plus x. and then you distribute on the right hand side to get negative x cubed plus x, and there you go. You see that they are equal, so we know this is an odd function because f of negative x is equal to the opposite of f of x. So once you prove it's odd, you don't have to check for the even. Okay. Once you figure out one of them, you don't have to do the other. So that is it for this section of graphs of functions part 2. So be prepared in class to have some of these discussions about what is the rule for symmetry to the x-axis, and then also what is the only function that is symmetric to the x-axis.